Alright, so we have a tire here, and it's rolling down some sort of incline. Now, this is a typical problem of something rolling down a hill, except there's this extra force term here, which I've added on. Uh, just nothing, it's not representing anything in particular. It's just some force that's acting on the tire and in this whole area. So we also have gravity, the gravitational force here. So what we're going to do is use work energy uh, to find out what the final velocity of the tire is when it reaches the end of the hill. So first off, we're going to find out first if this force up here is actually conservative. Otherwise, work energy wouldn't really work. So if we take that force, and in order for F1 to be conservative, uh, the curl of the force would have to be equal to 0. So if we take the curl of the force, we find out that in fact the force is conservative, in that we get the curl of the force is 0. So we should be able to safely use the work energy setup that's usually used, where you take kinetic energy plus potential energy equals the total energy done, total work done, which would be 0. So then we need to find the kinetic energy of the tire, and we include the normal 1/2 mv squared for typical kinetic energy, but there's also rotational energy, so we have to include the 1/2 I omega squared. So the moment of inertia for the tire is mr squared, and omega is the velocity over the radius of the object. So if we plug that into the kinetic energy formula, we get that the kinetic energy portion is mv squared, because some stuff cancels. And then we need to find the potential of the system. So for potential, we have gravitational potential, and we have that other force's potential. So if we just add those together, we have the total potential. So if we solve for the kinetic energy from the equation above, we can plug in the kinetic and potential energies, and the masses cancel, and we get this here. And then if we take the square root on each side, we get an equation for velocity, where it's the square root of g y minus alpha x cubed over 3 plus beta x squared over 2. And if we plug in the numbers from above, we get that the final velocity is 3.42 meters per second. And we can check the units of this equation here. So g is meters per second squared times meters, and then minus 1 over meters squared 1 over meters second squared. That's the units for alpha. X cubed would be meters cubed, plus the units for beta are 1 over second squared times meters squared, and we just end up with, and that's all taking the square root of, and then we end up with the square root of meters squared over seconds squared, and you take the square root and you get meters per second. So that makes sense. And if we didn't have that F1 force, um, T equals, we just solve that quickly, and we get that the velocity would be equal to the square root of g times y, and the velocity would be 4.43 meters per second. And that makes sense because if you didn't have that force up here, the ball would roll down faster because the force is going this way, so it slows down the ball as it rolls. And that's pretty much it.